Welcome to the second part of lecture 3 in bmb540. In the first part of lecture 3, in the video, you were introduced to a new quantity called the Gibbs free energy. And the reason we introduced this quantity is because it gives us, in a single equation, the direction of spontaneous change for any process. Okay, so this slide is a reminder of what we have done so far. The different types of processes on the left, and there are different types of functions. There are state functions, and there are functions that are not state functions. Entropy, like the internal energy, the enthalpy, is a state function. The Gibbs free energy is also a state function. Pressure, volume, and temperature are state variables, so they define what a state is. So, of course, they are independent of how you got there. Heat and work are not state variables, they depend on how you got there. So as defined in the previous lecture, the Gibbs free energy is the difference between the enthalpy and the product of the temperature and the entropy. If you write it in differential form, at constant temperature and pressure, it becomes dH minus T ds. And for a process going from point 1 to point 2, the difference in Gibbs free energy is the difference in enthalpy minus the temperature multiplied by the difference in entropy at constant temperature and pressure. So these are very important equations and you should memorize them, know them. At equilibrium, the change in Gibbs free energy is zero. And away from equilibrium, systems evolve such that a differential change in Gibbs free energy is less than zero. This is best illustrated by this figure from Korean. So on the left hand side on the top is the Gibbs free energy. On the x-axis is the progress of a reaction or process which is occurring at constant temperature and pressure. So let's say you're at point B. If you zoom in, we all know the equilibrium is at point A because this is where the dg is equal to 0. We'll come to that. So if you're at point B, you will reach equilibrium if you go towards point A, but not if you go above B. So if you go from the central point here to the red region, if you go above, the change in Gibbs free energy dg will be positive because you're going from a lower value to a higher value. On the other hand, if you come down, you'll be going from a higher value to a lower value, and therefore dg will be negative. And this is the direction of spontaneous change because it brings you closer to equilibrium at point A. If you zoom into point A now, this point is at equilibrium because the change in Gibbs free energy with respect to the variable x is 0. So the slope dg by dx is 0 at this point. So if you make a small change in x to go either left or right, the system will bring you back towards equilibrium because dg, whether you go to the left or right, the dg will become negative and it will pull you back towards equilibrium. You can interpret this graph as if putting a ball at point B and it will eventually arrive at point A. Of course, this graph shows Gibbs free energy as a smooth, almost parabolic curve versus x. Usually, this is not the case, but for illustrative purposes, this is enough. So the equilibrium is achieved when dg by dx equal to 0, but this is not entirely accurate. dg by dx is 0 defines actually a maximum or a minimum in g with respect to x. So in this plot here, we have 2 points where dg by dx, or the slope of g versus x, is 0, point A and point B. At point A, small changes away from A will bring you back towards equilibrium. At point B, if you make a small change away from point B, you will either go to A or you will go in the other direction. So this is an unstable point, while A is a stable equilibrium. Very good. The units of free energy are energy per mole. At constant pressure and temperature, the quantity, the free energy which is relevant is the Gibbs free energy, defined as H minus Ts. At constant volume and temperature, you have A, which is the Helmholtz free energy, and this is the difference between internal energy and the product of temperature and entropy. If you remember Internal energy is the heat transferred at constant volume, while enthalpy is the heat transferred at constant pressure. So for any process occurring at constant temperature and pressure, the spontaneity is described by a balance between the change in entropy and a change in enthalpy, especially for biological systems. And I will show you a couple of examples of this. Before that, this is how equilibrium would be achieved. If you have G, or entropy, on the y-axis and progress of change on the x-axis, the Gibbs free energy will be minimum, while the total entropy of the universe will be maximum at equilibrium. So for biological systems, what are the contributions or interactions which contribute to the change in enthalpy? These are typically non-bonded interactions for biological molecules. The bonded interactions don't change very much unless there is a reaction occurring, but the non-bonded interactions change, and these non-covalent interactions are either hydrogen bonding, electrostatic interactions, or van der Waals forces. Hydrogen bonding is essentially a type of electrostatic interaction, and Daniel has covered these forces in class. All of these are of the magnitude of thermal energy, so they're very, very small. Here Kb is the Boltzmann constant and T is temperature. So these are very, very small forces, but when they work in concert, they can lead um, to self-assembly and evolution of biological systems. So let's take a few examples of spontaneity. Um, so in this figure on the left, you see sodium-potassium pump. This is a simulation snapshot of the sodium-potassium pump embedded in a lipid bilayer. On the bottom, you have inside the cell, and at the top, you have outside the cell. And in the middle, you can see these three yellow spheres. These are ion binding sites. So now I'm going to play an animation from a molecular dynamics simulation, which I have showed you earlier as well, where a potassium ion, which is free in water, spontaneously binds to this ion binding site located inside the protein. So it eventually finds this ion binding site. So when you look at such a spontaneous process, one should analyze what are the enthalpic and entropic contributions to this process. In this case, maybe the next figure will make it clear. Right, so this is some details of the ion binding site. So in this figure, you can see 4 amino acids which bind to these 2 ions. And now when the 2 ions are not bound, these 4 amino acids are probably conformationally more free, so they have higher entropy. The same is true for the ions. They are free in solution, but when they bind to the protein, their entropy is significantly reduced. So this spontaneous ion binding may not be entropically favorable, but the strong electrostatic interactions between these ions and the amino acids make a very big enthalpic contributions, so that the enthalpy dominates and the negative change in entropy does not dominate. So the enthalpy change is very, very negative, and therefore this process is spontaneous. There may be some other details involved. For example, these ions might still fluctuate inside the ion binding site and may have some entropy, but we will not go into the details of these. Okay, so you were not supposed to see the results of this, but anyway, for spontaneous ion binding to a protein, a positively charged ion binds to a negatively charged amino acid. Which quantity dominates? Delta G. So most of the students in a previous lecture last year thought it was entropy, but in fact it is enthalpy which is dominant because of the electrostatics. Here is another process, the self-assembly of lipids into a lipid membrane. Here too, there is a balance of enthalpic and entropic forces. Once a membrane is formed, the lipids form very strong van der Waals contacts with each other. So this is enthalpically definitely favorable. The water, before the lipids self-assemble, is ordered around each hydrophobic lipid tail. So the water molecules have low entropy before the self-assembly and have higher entropy after the self-assembly when they are free to move around in the aqueous phase. For the lipids, it is opposite. The lipids were more conformationally free in the dissolved form, so each tail could fluctuate freely, but in the lipid membrane, each tail cannot fluctuate freely. It is confined inside the membrane, so the entropy of the lipid would actually decrease. So there are three factors at play. The hydrophobic effect, which is the entropy of water. So the entropy of water increases upon self-assembly. The entropy of lipids decreases. But there is also a strong enthalpic contribution, which is mainly the van der Waals interactions between the lipid tails. So for biological molecules, conformational freedom is something you should remember. Um, if a drug, for example, or a ligand binds to a protein, the ligand's entropy is higher in the aqueous phase but lower when it is bound to the protein. As homework, please read pages 894 to 897 in Korean. It has an excellent discussion about the enthalpic and entropic contributions of DNA hybridization. So when two DNA strands come together and form spontaneously a double helix in water. So please go through this and perhaps discuss this with a classmate. Another very important concept attached to the Gibbs free energy is that the Gibbs free energy gives you the maximum non-expansion work that can be extracted from a system at constant pressure and temperature. You can go back and try to repeat what I just said. And this concept becomes very important, for example, when you're trying to calculate the amount of work that a motor can extract from um, a proton motive force, for example, stored in the mitochondrial membrane. So the different kinds of work that can be done or can be done by a system or on a system. In general, of course, force is work is force multiplied by displacement integrated. The expansion work, which we have talked about so far in this course, is pressure times the change in volume. This essentially is derived from the equation above. Electrical work is work done by when you move a charge against an electrical potential. And I'll give you an example of this in a little bit. Surface tension work and stretching work are essentially variants of expansion work. Surface tension work is two-dimensional work, work done against surface tension, just like you do work against an external pressure. And then there is line stretching work, like you stretch a rubber band, and this is also a one-dimensional expansion work, a variant of a one-dimensional expansion work. But for biological applications, what is really important is one, electrical work, and the second, chemical work, which is work done against a chemical potential. So when you take a molecule from a low concentration to a high concentration, you must do certain work. I will introduce chemical potential in the coming lectures. Here is an image which shows you a schematic of a sodium-potassium pump. This is a sodium-potassium pump in gray, and it transports three green or three sodium ions against their concentration gradient across the membrane. And at the same time, it transports two red potassium ions, again against their concentration gradient um, across the cellular membrane. Now, in both cases, the pump is doing chemical work because it needs to transfer ions against their concentration gradient. In one case, it is also doing electrical work because it is transferring an ion against the electrical potential. In the other case, it is not doing this electrical work. So there is electrical work being done and chemical work also being done. So a couple of examples related to the Gibbs free energy and the maximum non-expansion work. Here is an example you can look at in Atkins. Suppose a small bird has a mass of 30 grams. How much glucose must it consume to fly 10 meters above the ground? You can assume that the change in Gibbs free energy that accompanies the oxidation of 1 mole of glucose is this quantity at 25 degrees centigrade. So the idea behind doing this is you calculate the work done as the mass multiplied by the gravitational constant multiplied by the height. So this is the total amount of work that you can extract. And this image from my notes shows you that. So the maximum non-expansion work is mass multiplied by g multiplied by h. And the reaction Gibbs free energy, or the change in Gibbs free energy, is about 2808 kilojoules per mole. So the number of moles of glucose required is mgh multiplied by delta Rg, because remember this is kilojoules per mole, and the mass of glucose is this quantity multiplied by um, the molecular weight of glucose. And if you calculate this, please don't look at the if you just put in the numbers, you find an answer about the number of moles of glucose that are required to the mass of glucose that the bird must consume, and this is about 1.9 into 10 to the power of minus 4 grams, which is a few milligrams. I'm sorry, this is not visible in the slide, but this example is there in Atkins. You can take a look. Here's another example. A hard-working human brain such as yours, which is grappling with this annoying physical chemistry course, is operating at about 25 joules per second. So this is the amount of energy it is consuming. So what amount of glucose must you consume? So how much must you eat before a physical chemistry class so that your mind can stay active? The answer is 5.8 grams, and here is the solution. In 1 hour, the total energy required is the energy required in 1 second multiplied by the total number of seconds. So this is so many joules. The amount of glucose, the amount of energy provided by 1 mole of glucose is 2808 into 1000, because remember it was 2808 kilojoules. So the number of moles of glucose required is this number divided by this number, and the mass, of course, is the number of moles divided by the molecular weight of glucose. So this is about 6 grams of glucose for an hour. Doesn't sound like a lot. In reality, of course, biological system can extract 40 to 50% of the total available Gibbs free energy. Oh, this slide is wrong. It's not available energy, but available Gibbs free energy when it consumes glucose. A combustion engine, such as in a car, would only be able to extract 5 to 10%. So biological systems are very, very efficient in extracting energy. So in fact, you must eat about 12 grams of glucose. But this is, of course, only the energy that will be consumed in the brain, assuming it is at 25 joules per second. You will also need more glucose because you will do work while breathing, talking, and so on and so forth. Okay, so this concludes the second part of lecture 3, which was an introduction into the Gibbs free energy, the approach towards equilibrium, and that the change in Gibbs free energy is related to the maximum non-expansion work in a process occurring at constant pressure and temperature. In the next lecture, we will start with the reaction Gibbs free energy, and time permitting, also talk about the fundamental equation of chemical thermodynamics. All right.